You know that feeling, right? You're deep into a long polynomial calculation, and one tiny mistake just throws the whole thing off. It's so frustrating. Well, today we're diving into a powerful shortcut that makes those problems so much cleaner and honestly way faster. It's called the Remainder Theorem, and trust me, it's about to become your new best friend in algebra. So let's just set the stage here with a super common problem, evaluating a polynomial. You get a function, you get a number, and you just plug it in. Sounds easy enough, doesn't it? But with all those exponents and different terms, it is just so easy for one little slip up with a sign to completely derail you. Okay, take a look at this function. To find f of 3, you've got to plug 3 in for every single x. That means you're cubing it, then squaring it, multiplying, adding, subtracting. It's practically a minefield for arithmetic errors. But what if I told you there was a way to get the answer that avoids all that mess and just gives you one clean final number? Well, that better way is the remainder theorem. And it's a really elegant, simple idea that connects that messy problem of plugging in numbers with the super clean process of polynomial division. So here it is, the big idea. It says that when you divide a polynomial by a simple factor like x minus c, the remainder, that little leftover bit at the end, is the exact same value as if you'd plugged c into the function. Just think about that for a second. Instead of all that substitution, you can just divide and look at the remainder. It's a complete game changer. So let's break it down. On the left, you've got method A, direct substitution. That's the old way. Yeah, it works, but it's messy, and it's where mistakes happen. But on the right, you've got method B, using synthetic division. This is our shortcut. It's clean, it's organized, and it is built for speed and accuracy. Okay, so we've got this awesome shortcut. But what happens when the remainder isn't just some random number? What happens when it's 0? This is where the theorem really levels up, going from a neat trick to an absolutely essential tool for solving equations. All right, let's put this thing to the test. We need to find f of 2 for this polynomial, but we're not going to plug in 2. Nope, we're going to use our shortcut and divide the whole thing by x minus 2 with synthetic division. And remember, the only number we care about is the remainder. Okay, so here's how it works. We put our c value, which is 2, out front in that little box. Then we write down the coefficients of our polynomial. And notice we have to put a 0 in for that missing x term. Can't forget that. Then we just bring down the first number, multiply, add, and boom, look at that final number. Our remainder is 0. So according to our new theorem, that means f of 2 is 0. But a remainder of 0 tells us something way more important than just the answer. It tells us something absolutely critical about our polynomial. Any ideas what that might be? And this brings us to the factor theorem, which is really the superpower we've unlocked. It's a special case of what we've been doing. A remainder of 0 doesn't just mean the answer is 0. It means you've found a factor of the polynomial. And if you find a factor, you've found a root or a solution. This is literally how we crack open complex polynomials and solve them. Okay, so the rule is simple, right? 0 remainder means you found a factor. Let's use that rule to tackle a classic exam-style question, and then we'll look at the number one trap that people fall into with this stuff. So here's a question you'll definitely see. Is x minus 3 a factor of this polynomial? We don't need to do long division. We don't need to try and factor it by hand. We just need to check one single thing. Do we get a remainder of 0? So we set up our synthetic division, this time with c equals 3. We run through those same easy steps. Multiply, add, and we get to our remainder. And this time, it's 16. And just like that, the answer is crystal clear. Since the remainder is 16 and not 0, we know for sure that x minus 3 is not a factor. And hey, bonus info. Thanks to the remainder theorem, we also know that f of 3 equals 16. We got 2 answers for the price of 1 calculation. Now listen up, because this is the number one spot where people get tripped up. It's so simple, but it's all about the signs. Forgetting this rule can send your whole answer in the wrong direction. Okay, check this out. The factor and the 0 or root always have opposite signs. So if the factor is x minus 3, the number you test is a positive 3. If the factor is x plus 2, the number you test is a negative 2. Lock this in your brain, seriously. It will save you so many points.
Ready for a pro-level problem? This time we've got an unknown, this k, sitting inside the polynomial. But don't worry, the logic is exactly the same. We are told that x plus 2 is a factor. And what does that mean? It means that f of negative 2 must equal 0. So all we do is plug in negative 2, set the whole thing equal to 0, and solve for k. And in this case, it turns out k is just 0.
So why are we spending all this time on this? Why does it matter so much? Well, it's a lot more than just a neat trick for algebra class. This theorem is a fundamental building block for solving much bigger and more complex problems. Think of this as your gateway. It's how you can quickly test for roots, which is the whole key to factoring those messy higher-degree polynomials. It also leads directly to more advanced ideas, like the rational root theorem, which is what gives you a list of possible roots to test with this very method. And this is not just for math class. In the real world, engineers use polynomial models to describe really complex systems. This theorem gives them a lightning-fast way to check if a critical point has been reached, like say if the stress on a bridge hits its failure point, without having to run the entire complicated calculation from scratch. So, we've totally mastered this incredibly fast way to test if a number is a root. But that leaves us with one huge question, right? Where do we even get the list of numbers to test? How do you even start to guess what the roots of some crazy polynomial might be? Well, that is the next step on this journey, and it all builds right on top of the foundation we've built today.